Welcome to AQA GCSE Chemistry Paper 2 walkthrough. This is the 2021 and it's for Paper 2. Okay, question 1. This question is about chemical analysis. The student tested copper sulfate and calcium iodide solution using flame tests. This is the method used. Dip the metal wire in copper sulfate solution, put the metal wire in a Bunsen burner flame, record the flame color produced, repeat it using calcium iodide solution. Which color flame is produced by copper sulfate? Make sure you use a highlighter when answering these questions. Copper ions go green when they are in a flame. Calcium compounds produce an orange-red flame color. The student left out an important step before reusing the metal wire. The student's method did not produce a distinct orange flame. So you normally get a red-orange flame with calcium ions, but the saying here, the student didn't get it. But they didn't clean the wire. They should have dipped the wire in hydrochloric acid, or you can just say clean the wire in between uses. And what's the reason? Because the impurities, like the copper ions from the first test, the green flame would disguise the orange flame or confuse, you get a mixed flame color. So basically, if you don't clean the wire, you can't be sure which ion is causing the flame. Is it the one from the first test or the one from the second test? Yeah, let's move on. 1.3. Here we go. If you can hear my kids in the background, I'm just trying to rush to get this out. Make sure you pause the video at the start of each question, guys. That's really important, and you have a go yourself. 1.3, the student added sodium hydroxide solution to copper sulfate solution and calcium iodide solution. Give the results of this test. This is the precipitate test. So when you add sodium hydroxide to certain metal ions, like copper forms a blue precipitate, a blue solid. If you add it to calcium ions, which would be found in calcium iodide, you get a white precipitate. And this is the equation you have to know if you're doing higher trips. Cu2 plus 2H minus, that's the hydroxide ions, form copper hydroxide, a solid, because it's a precipitate. A precipitate is a solid that forms within a solution. So, and then we've got calcium ions plus hydroxide ions make CaOH with a little 2 outside, and it's a solid. And don't forget, in these equations, if you're asked to write an ionic equation and they want state symbols, you've got to put AQ. All right, we're going to move on to 1.4. To test for sulfate ions, the student added dilute hydrochloric acid to copper sulfate solution. Name the solution that would show the presence of sulfate ions when added to this mixture. So they're saying, if you basically, what do you add in the test for sulfate ions? Yes, you add acid to get rid of impurities. The hydrochloric acid actually gets rid of carbonate impurities that might be there. And then you add barium chloride. So your answer is barium chloride. You can write BaCl2, or you can just write barium chloride. And the barium 2 plus ions react with the SO4 2 minus ions to form barium sulfate, which is a white precipitate, an insoluble white solid. 1.5. To test for iodide ions, the student added dilute nitric acid to the calcium iodide solution, getting rid of impurities. Name the solution that would show the presence of iodide ions when added to this mixture. So the iodide is a halide, an ion from the halogens, and we add silver nitrate. You can write AgNO3 with an AQ, or you can just write silver nitrate solution. And you get a white solid with chloride ions, a cream with bromide ions, and we get a yellow solid if there's iodide ions, I minus ions present. And what is that yellow solid that forms? Well, if you do Ag plus I minus, you get AgI, that's the solid. But your answers here are just silver nitrate solution and a yellow solid forms. Okay, let's move on. And that's the end of the first question. Let's get into the second one. This question is about water. In the UK, potable drinking water is produced from different sources of fresh water. Explain how potable water is produced from fresh water. Potable water is any water you can put in a pot, like a cooking pot, or you can drink, safe. And basically, we make it when it rains, you get ground and surface water, or you get rivers and lakes. And you can't just dip your glass into a river or lake and have a drink. You got to filter it first. So the first step is filtration, and that removes twigs or stones. Use gravel and sand, known as a bed, to filter it. And that removes the small debris or solid bits. We've then got to sterilize, which means kill bacteria or pathogens. We can do that with chlorine, ultraviolet light, or O3, which is known as ozone. The same stuff you've got in the atmosphere. Okay, and so these are your answers for 4 marks. Don't forget to pause the video at the start of each question, peoples. 2.2. A different country has very little rainfall, a long coastline, but loads of energy. We're talking Dubai, somewhere, the UAE, something like that. Suggest a process the country could use to get potable water. Look, it doesn't rain, but they can use reverse osmosis or distillation, where you just take the seawater and you evaporate the water and condense it, and you've got salt-free water. Okay, wastewater is not fit to drink. This is the water that goes down the floor of your shower. Treatment of wastewater produces two substances, liquid effluent and solid sewage sludge, and it's also the water from your toilet. The liquid effluent we break down with aerobic bacteria, and the solid lumps, we break down with anaerobic digestion. Cut myself off there. That was anaerobic digestion. Right, let's go. 2.4. Table 1 shows information about the disposal of processed solid sewage sludge in the UK from 1992 to 2010. So calculate the percentage of processed solid sewage sludge that was burned in 2010. Give your answer to 3 sig. Well, if we circle 2010, we go along and look how much was burned. It was 260. The total amount of sludge was 1413. So what's the percentage of 260 out of 1413? 260 divided by 1413 times 100. What is that? What's my calculator? Okay, it's 18.40 on my calculator. But what I need to do is round that to 3 significant figures. So we're just doing 18.4%. Lovely. Okay, let's move on. You might hear my crazy kids in the background, but that is just doing this on the weekend and trying to get it done before the exam. So 2.5 suggests one reason why the total mass of processed solid sewage sludge increased between 1992 and 2010. Well, obviously, the human population is increasing all the time. So there is a hell of a lot more people doing solid poos. Yeah, basically, human population has increased. Okay, between 1992 and 2010, the proportion of processed solid sewage sludge used as fertilizer increased. So why are we increasing using the amount of solid sewage sludge as fertilizer? Well, we want to grow more crops, and again, we have an increased population, which means we need more food, so we need more crops. And therefore, if we need more crops, there is an increased demand for fertilizer. More people gardening, more people using fertilizer. So there's an increased demand for processed solid sewage sludge as fertilizer. Yeah. And maybe more people are swapping to organic fertilizer, which is what you get when you use waste rather than chemical fertilizer or artificial, which is made in the laboratory. Also, by using the solid waste as fertilizer, you don't have to dig it into the ground and bury it as much. So less having to bury the poo in the ground as it's being put on the crops. Question 3 is about hydrocarbons. Hexane and hexene are hydrocarbons containing 6 carbons in each molecule. Hexane is an alkane and hexene is an alkene. Draw one line from the hydrocarbon to the formula of that hydrocarbon. So hexane is an alkane. You need to know off by heart the general formula for alkanes, which is CnH2n plus 2. So all we got to do, it tells us in the question there are 6 carbons. So we just have to go to find out the hydrogens. We just do 6 times 2 plus 2, and that is 12 plus 2 is 14. So we're looking for the formula C6H14 for hexane. And you'll find that one just down here. Now let's go and do alkenes. So alkenes have the general formula, you need to know it off by heart, CnH2n. So if C is 6, what is H? H is 12. So you just times it by 2, so H is 12. So we're looking for the formula which is C6H12, and just draw a line from hexene to that one. Boom! Let's move on. 3.2. Bromine water is added to hexane and hexene. What would be observed when bromine water is added to hexane and hexene? Right, bromine water, Br2, becomes a halogenoalkane when it's added to alkenes. However, and that's an addition reaction. However, with alkanes, unless you've got ultraviolet light, which it doesn't say you have here, it will not add to them. So with alkanes, the bromine water stays orange, and with alkenes, it goes colorless as it forms a halogenoalkane. Okay, here we go. We're looking at 3.3. Ethane is an alkane and ethene is an alkene. Figure 1 shows the displayed structural formula of ethane and ethene. Compare ethane and ethene. You should refer to the structure and bonding and their reactions. Okay, let's go through the differences. So both are hydrocarbons. They both only contain carbon and hydrogen only. Okay, so that's going to get you a mark because that's a similarity. Another similarity we can find, or both contain two carbon atoms. See, they both got two carbon atoms. However, ethane has six hydrogens and ethene only has four hydrogens. So when you're doing a comparison like this, you want to say what's the same and what's different. Um, so yeah, one's got six hydrogens, one's only got four hydrogens. Now, both contain covalent bonds. They're those solid black lines you can see here, carbon hydrogen bonds. So both contain carbon hydrogen bonds, I could have written. But ethane has a CC single bond, whereas ethene has carbon hydrogen bonds and it has those C double C bonds. So the C with the two line bonds, they're called double bonds. And that means that ethene is unsaturated, whereas ethane is saturated. Okay. Or unsaturated if you contain a double bond. Oh my gosh, my writing doesn't show up here. You're just going to have to listen to these answers. Both will burn in oxygen. Now, it asks us to consider their reactions for the final point. So, both will burn in oxygen to produce carbon dioxide and water. However, with alkenes, you're more likely to get incomplete combustion, and that's because there are more carbons compared to the hydrogens in alkenes. Look, it's a 1 to 2 ratio from carbon to hydrogen, whereas it's like a 1 to 2.5 ratio or something with the carbon to hydrogen with ethane. Okay, so and also ethene will decolorize bromine water, as we just talked about in the last question, whereas ethane won't decolorize bromine water. Um, what other things? Alkenes are far more reactive than alkanes because alkanes just basically are used as fuel, so they can just do combustion. Ethene, if you're doing trips as you are, can be turned into alcohols by hydrating it. Okay, by adding water, you can turn them into alcohols. Ethene can be turned into polyethylene, a plastic, by addition polymerization, catalyst, and pressure, and you can squeeze them together. Ethene can also be turned into ethane by doing something called hydrogenation or hydrogenation. Yeah, that's right. Nickel catalyst and adding hydrogen, you can turn ethene into ethane. So there are tons of reactions that these alkenes can do. We can make alcohols, we can make plastic polymers, and we can make alkanes. I can't fit this on, guys, so you're just going to have to play it back and listen to the answers. But there's like 10 marking points there. So let's move on. Question 4. Yeah, we're looking at a dye here. You can see it's the old chromatography. And what's happened here, figure 2 shows the chromatogram obtained when someone puts some dye on the start line. We can see we've got two types of dye. It's split the chemical into blue dye and yellow dye. It tells us that the RF value of the yellow dye is 0.60. The distance moved by the yellow dye is 5.7 centimeters. Calculate the distance moved by the solvent. So you have to know the RF. Bada bada bing, bada bada bong. You have to know the equation for this, which is RF value is equal to the distance traveled by the dye divided by the distance traveled by the solvent front. So we're now going to do 5.7 over the mystery number, the distance by the solvent front, or 0.6, the RF value equals 5.7 over the distance moved by the solvent front. I always like to picture these in a magic triangle. So 5.7 would be at the top and 0.6 and distance moved by the solvent would be at the bottom. So we just want to do 5.7 divided by 0.6 and we're going to get D, distance moved by the solvent front. And so your answer should be 9.5 centimeters because the solvent front has to move further than the dye. 4.2, the green ink contains more than two compounds, suggests one reason why only two spots are seen. Okay, so at first you might think only these two are soluble in the solvent, but actually that's not really, if it was insoluble, we'd see a dot on the line. So that's not true. So what it is that only these two have color. You might actually have some colorless substances in there. Remember, if they were insoluble and had color, we'd see them on the baseline. They'd stay there as a dot in the middle of the baseline where you put the starting material. So actually, there might be some hidden spots and only these two can be seen. The other suggestion is that they have the same RF value as these two spots. So like you might have a yellow color hidden behind the blue and yellow dye. So there might be a third color that's hidden behind one of those because it has the same RF value and moved the same distance. Right. 4.3. On the chromatogram, the yellow and blue dots are very close together. How could you get them further apart? We'll use a different solvent for a start and or allow the solvent to travel further. The further the solvent travels, the bigger the difference in their solubilities will be shown because there'll be a bigger space between them. The manufacturers of the green dye use the same proportions of yellow and blue dye. Why? Well, they want the same color green each time they sell their ink for making t-shirts and stuff. They want it to be the same color, so it needs to be in the same proportions. It's a formulation. The RF value of the dye depends on the solubility of the dye in the solvent and the attraction of the dye to the paper. What will definitely produce a smaller RF value if the solvent and paper are both changed. So if we don't want it to move as far, we want it to have a greater attraction to the solid and less attraction to the solvent. So, and we also want it to be less soluble as well. So if it's less soluble and more attracted to the paper and less attracted to the solvent, then it won't move as far and we'll get a smaller RF value. This question is about materials used to make food plates. Food plates are made from paper, polymers, or ceramics. Table 2 shows the information about the plates of the same diameter made from each of these materials. So for like paper, it tells us it's made of wood. You can get 500 in a box. You can only use it once. It's biodegradable and recyclable. And then you've got the polymers from crude oil, 100 in a box, but you can use each one 400 times. So, yeah. Suggest two pieces of information about energy usage, which would help us to make a full life cycle assessment. Well, we haven't got the energy of transport. How much does it cost to transport the materials to the shops or wherever from where they're dug up to the factories where they're made? So we haven't got the energy of transportation. We haven't got the energy of extraction. Does it cost more energy to extract a certain amount of crude oil than wood or to mine clay? So we haven't got that. We don't have the production energy. So what about when you turn wood into paper? How much energy does that use? We don't know. So we don't have production energy and we don't have the energy needed for recycling. They tell us whether they're recyclable and two of them are, but does it cost more energy to recycle plastics or more energy to recycle paper? Okay, 5.2 or yeah, evaluate these materials for making food plates. So remember, when you see an evaluation, it's all about the for and against for each material. And there's going to be good and bad about each, and finally make your own judgment. And this is only a 4 marker, so it's kind of nice and easy to. Okay, let's go. Once again, sorry about hearing my kids in the background. I'm smashing this out while the kids are playing. So, plastics can be reused many times. Okay, so you can use plastics and ceramics the most. You can use ceramics, it said in the table, about 1,000 times compared to plastics 400, and paper can only be used once. So, that's obviously a downside to paper. However, a good thing about paper is that paper is renewable, whereas plastic and ceramics are both finite, meaning they're not renewable resources. Although we could recycle the plastics can be turned into bottles and things. So that should be added. The ceramic is the only one that can't really be recycled or renewed. Like you can't dig up more of the clay minerals once they're out the ground. Plastic and ceramic are not biodegradable as well. That's a bad point. The plastics in the ceramic will not break down naturally in the environment, and so you're going to have to dump them in a hole in the ground in landfill unless you burn the plastics, which releases pollution. But paper can be is biodegradable on the whole, so it will break down and go back into the soil, so less space taken up by landfill. So we've got loads of good points here. We'd have easily scored 4 marks as long as we finish with a judgment. Now there are tons of other marks on the mark scheme. You can check the link to the mark scheme in the description. I'm not going to go through all of them, but when you're doing an evaluation, always save a final point for your judgment. So try to make it separate, but I can't be bothered because I'd have to go look at the mark scheme. But overall, ceramic is better, I'm going to say, because it can be used 1,000 times. So likely it's going to save on energy, but that's my judgment there. Okay, let's move on. So for 5.3, it just says describe how ceramic food plates are prepared from clay, basically, or produced from clay. You just take wet clay. You might have used clay to make something before, and then you heat it in an oven so that it basically hardens. You can call it just heat it, you can say, but the correct term is a kiln. It's a type of oven where we heat clay. The question is about atmospheric pollution. Figure 3 shows limestone carving, which has been damaged by atmospheric pollution. The carving has been blackened by soot, um, eroded where the limestone has reacted with atmospheric pollutants. First of all, explain why soot is formed when some fossil fuels are burnt. So it's made from insufficient oxygen. A lack of oxygen, we get incomplete combustion. So that happens in car engines when cars are driving about. You get some incomplete combustion, and soot is actually solid atoms or particles of carbon called particulates. And here's an example. You've got methane plus oxygen, and it could make solid carbon if there's not enough oxygen and water. And yeah, you get solid carbon instead of getting carbon dioxide. Okay, let's move on. So your answer really here is incomplete combustion and from solid lumps of carbon or particles of carbon. Fossil fuels are burned in car engines. Explain how reducing the amount of sulfur in fossil fuels reduces the erosion of limestone. So essentially, when fossil fuels are burnt, fossil fuels contain a little bit of sulfur, right? Hidden within the fossil fuels, a bit of a mixture. The sulfur combines with oxygen in a reaction, which is sulfur plus oxygen makes sulfur dioxide. So that's S plus O2 goes to SO2. So you're going to get a mark for showing that sulfur mixes with oxygen to make sulfur dioxide when fuels are burnt. Sulfur dioxide is a gas. It rises up, mixes with water in the clouds. It forms acid rain. When it rains down, the acids react with the carbonates that are in the rock. Now, limestone is like calcium carbonate, or it's a type of carbonate. So when the acid rain reacts with it, um, yeah, it erodes the limestone. Why does it erode it during the reaction? Because a carbonate and acid reaction always form carbon dioxide as a waste gas. So you're losing some mass. You're actually losing mass of the statue is going off into the atmosphere. And so there you go. That's your explanation as to how sulfur in fossil fuels causes erosion. And if we can reduce the sulfur, then we can reduce the amount of erosion. And we can reduce the sulfur dioxide by reacting it with calcium oxide or calcium carbonate as it leaves the factories. So as the sulfur dioxide leaves power stations, they can spray it, the flue or the chimney of the power station, with calcium oxide and neutralize that acidic gas on the way out. Hokey dokey. There's the balanced equation for what's going on when a statue's breaking down, essentially, or something similar to that. So for 6.2, oxides of nitrogen are atmospheric pollutants which are formed in car engines. Explain what oxides of nitrogen are formed in car engines. Essentially, you need to say here nitrogen from the air. Whoops, sorry about that. You need to say nitrogen and oxygen from the air. They basically come down and they combine on the heat, on the hot of the car. The metal in the car engine kind of acts as a bit of a catalyst. But the nitrogen and oxygen combine from the air in the hot car engine to form nitrogen oxides. You can get nitrogen monoxide, trioxide, dioxide. Here's the formation of nitrogen trioxide. nitrogen and oxygen from the air, forming nitrogen dioxide, which of course causes respiratory problems and also contributes to acid rain. It forms nitric acid with water in the clouds. You have to know that also. Lowers the pH of soil and rivers and lakes, killing trees and fish. This question 7 is about carboxylic acids. Carboxylic acids belong to a homologous series. Table 3 shows information about the first 3 carboxylic acids, and this is a homologous series. So we've got methanoic acid, ethanoic acid, propanoic acid is the third one, and the formula will be CH Um, yeah, and how will we know that? Well, what happens, CHOOH, what happens with each member of a homologous series? You add CH2. So if you're going backwards, just take off CH2. If you're going forwards, one jump in a series, add CH2 to the formula. And that's how you can work out the different formulas. And this is the displayed formula of methanoic acid. Once again, I got to apologise for my mad kids who are dive bombing each other off the sofa, as I'm supposed to be looking after them, but I'm persevering with getting an exam done for you guys. 7.2. Ethanoic acid ionizes in water. The equation for this reaction is CH3COOH, aqueous symbol, reversible symbol, CH3COO minus, aqueous symbol, plus H plus, aqueous. Explain how the equation shows that ethanoic acid is a weak acid. Well, straight away, you've got the reversible symbol. That's going to get you a mark. So that shows that it goes in both directions. It forms an equilibrium and it only partially ionizes. It doesn't completely ionize. If it completely ionized, we would have an arrow instead of the reversible symbol. Let's move on to 7.3. And 7.3 says a student adds a solution of ethanoic acid to zinc carbonate in an open flask on a balance. Explain what happens to the mass of the flask as its contents during the reaction. So what we would expect with ethanoic acid reacting with zinc carbonate, it's an acid and carbonate. We just talked about that with the erosion. We would expect carbon dioxide to be formed and carbon dioxide to leave the flask, hence the mass goes down. So we want to say that carbon dioxide is formed, it's a gas, the carbon dioxide escapes, reducing the mass of the contents of the flask. And that will get you your 3 marks. Ba-da-ba! And here is the equation for this reaction. Not that you need it to score the 3 marks. You don't need it. You just need what we've written there. So the equation is CH3COOH. That's ethanoic acid. You need to know that formula off by heart. Plus zinc carbonate, ZnCO3. And that is going to make zinc ethanoate, which is the salt that's going to be made. I'm not going to bother balancing this because you'd actually, yeah, I won't bother balancing it. Plus H2O plus carbon dioxide and gas that comes off. There we go. And that's why the mass goes down. Super. Let's move on to the next question. Okay, 7.4. The student compares the rates of the reaction of zinc carbonate with 0.01 mole per decimeter methanoic acid and 0.01 mole per decimeter ethanoic acid. The rate of reaction with methanoic acid is greater than the rate of reaction with ethanoic acid. Explain why. You should refer to the ions in your answer. So, although they have the same concentration, it is because methanoic acid has the lower pH, which means when you put it in a solution, it releases more hydrogen ions. All right, so it has a higher concentration of hydrogen ions. Even though the acid concentration is the same, the methanoic acid dissociates more, releasing more hydrogen ions, which means you're going to have more particles able to collide and therefore a higher rate of reaction. That was actually a particularly hard answer. So if you were baffed by that, do not worry. That was particularly hard. Okay, 7.5. Give the name of the ester produced when ethanoic acid reacts with ethanol. Ethanoic acid reacts with ethanol to produce an ester. This is an easy one to remember. So ethanoic acid and ethanol form ethyl ethanoate. That's the name of the ester. But when you're naming an ester, a more difficult one, the first word comes from the alcohol and the second word comes from the carboxylic acid. So what we want to say there is, for example, if we had propanoic acid and ethanol, the name would be ethyl propanoate. So the second word comes from the carboxylic acid. So it'd be ethyl propanoate. Yeah, esters are made when alcohols and carboxylic acids form. They've got really nice smells, esters. They're used in sweets and perfumes, cooking industry and perfumes. Right, hexandioic acid and ethanediol join together to produce a polyester. Ethanoic acid and ethanol join together in the same way to produce an ester. What is the displayed structural formula of the ester produced when ethanoic acid reacts with ethanol? So we're looking at the structure. So what I've drawn here is a molecule of carboxylic acid. And over here, I'm drawing the ethanol. So ethanol has two carbons, ethanoic acid has two carbons, but of course the carboxylic acid has that acid group. And what happens is we get a condensation reaction. And during this reaction, a water molecule is removed. You lose the OH from the alcohol. Sorry, you use the H from the alcohol and the OH from the carboxylic acid. That breaks off as a water molecule, like I've shown here. All you've got to do is redraw it, combining what's left together. So what I've done there, that's the remains of the carboxylic acid. Then in pink here, I'm going to write the remains of the alcohol, and they've bonded together, the O and the C double O. That's called an ester link or an ester bond. That functional group in the middle, the C double O and the O together are the ester link. And so that's this same formula as this one down here. Another thing about esters, I said they're used in perfumes and foods. And another reason other than their lovely smell is that they're volatile. They evaporate easy, and that's important when you want the smell to travel. So question 8, this question is about the rate of reaction between hydrochloric acid and calcium carbonate. A student investigated the effect of changing the size of the calcium carbonate lumps on the rate of reaction. This is the method they used. Pour 40 centimeter cubed of hydrochloric acid into a conical flask. Add 10 grams of small calcium carbonate lumps to the conical flask. Attach a gas syringe to the conical flask. Measure the volume of gas produced every 30 seconds for a total of 180 seconds. Repeat steps 1 to 4, but this time use 10 grams, keeping the mass the same, of larger calcium carbonate lumps. The student calculated the number of moles of gas from each volume of gas measured. This shows the student's results for the large lumps. We've got 0, 30, 60, 90, 120, 150, 180, 0, 0, 11, 0, 12, 0. Yeah, you got the idea. The student plotted the results for the small lumps on 4. You need to complete figure 4. You should plot the data for the large lumps from table 4 and draw a line of best fit. And we're going to get 3 marks for this. So I'm going to show you how that's done. So now we basically need to look at the table and plot the points onto the graph. So it's going to look something like this. Hold on. Plot the large lumps from table 4. Once you put all the points on and you work that out, you're going to get 3 marks. You can afford to get one of the dots in the wrong place, but essentially it's going to have this pattern, and then you're going to attach a line of best fit. And with the larger lumps, it's going to still produce the same amount overall because you've got the same amount of particles, but it's going to take a longer time to get there. So you're looking at a lower line, correct plots, ending at the same place. Okay, determine the mean rate of reaction for small calcium carbonate lumps between 20 seconds and 105 seconds and give the unit. So what we need to do here is go along to 20 seconds on our graph and draw a line up. So 20 seconds and draw a line across to where it meets the number of moles. And our number of moles is like 0.0, what is that? 0.0014, let's go with. And then let's go up to 100, draw a line across, draw it over to the y-axis. What have we got? Number of moles here is about 0.0038. And so we need to then do y over x. So we need to find the time. So I'm going to do 105 minus 20 equals 85 seconds is the time. That's our x-axis. And our number of moles of gas is going to be 0.0038 over, take away 0.0014 is 0.0024. So I need to do y over x. to find the average given off, and it's 0.0024 divided by 85, and that is going to give me calculate 2.8 times 10 to the minus 5, and the units for that are going to be moles per second. 2.8 times 10 to the minus 5, we divided the y by the x, which was moles, we divided it over seconds. The students concluded the large calcium carbonate lumps reacted more slowly than the small calcium carbonate lumps. How do the students' results show this conclusion is correct? Well, we can't see now because I've deleted my lines, but when we used the large lump, the curve was less steep or the line was lower, so either of those would get you the mark. The curve was less steep or the line was lower. Okay, 8.4. Calculate the surface area to... Hokey dokey. So we know the cube is 0.5. So if I want to find the area of one side of the cube, I do 0.5 times 0.5 is 0.25 centimeter squared. Times that by 6 because there's 6 sides. So I know the total surface area of the cube is 1.5 centimeter squared. The volume of the cube is 0.5 times 0.5 times 0.5, which is an eighth. What is an eighth? 0.125, but that is centimeter cubed. So my surface area to volume ratio is 1.5 to 0.125. We want whole numbers because it asks for a whole number ratio. So we need to divide by the smallest, and if we'll get 12 to 1. So 1.5 over 0.125, and we get 12 to 1. Okay, next question. A larger cube of calcium carbonate has sides of 5 centimeter. Describe how the surface area to volume ratio of this larger cube differs from that of the one we just did. Well, it's going to have a smaller SAV. Hold on, you say, but it's got a bigger surface area. Yep, but the volume is much bigger. So if we go 5 times 5 times 6 to get the surface area, we get 150 centimeter cubes surface area. Now, if we want to find out the volume, we go 5 times 5 times 5, which is 75 centimeter cubed. So it's actually only got a 2 to 1 surface area. So the SAV, the surface area to volume ratio, has gone way down from 12 to 1. Okay, 9. This question's about algae. A student placed algae in water containing dissolved carbon dioxide. They shone a bright light into the algae. Gas bubbles were collected as the algae photosynthesized. So we're being told they photosynthesize. That's because they're absorbing the carbon dioxide and they're making glucose and oxygen via photosynthesis. And they're using water. Describe a test that could identify the gas collected. What gas are they giving out? Well, in photosynthesis, we release oxygen. And so it's basically asking you, what's the test for oxygen? And the test is glowing splint relights. And that will get you 2 marks. 9.2, glucose is produced when algae photosynthesized. Name 2 naturally occurring polymers that can be produced from glucose. Well, cellulose, starch, or glycogen. I mean, I don't think the algae will make glycogen, but there we go. Cellulose, starch, and glycogen are all naturally occurring polymers of glucose. Show the displayed structural formula of an amino acid of glycine. So we've got an amino acid here with an amino group or amine group and a carboxyl group or carboxylic acid group, or acid group. How many functional groups are there? There's 2. Glycine reacts by condensation polymerization to produce a polypeptide and one other substance. So when you do condensation, you join 2 little molecules into a big one and you remove water, so you form water as well as the big polymer. 9.5. Scientists think that algae may have used gases in the Earth's atmosphere. Algae need an element to produce the molecule in figure 6, which is not present in water or carbon dioxide. Which 2 gases from the Earth's atmosphere could give this element? Right, well, the element is nitrogen. And what 2 gases were in the atmosphere that could provide nitrogen? Well, you've got N2, which is just nitrogen gas, and we've got NH3, which is known as ammonia. They both came out of volcanoes in the Earth's early atmosphere. The development of the function of algae are controlled by a naturally occurring polymer. Figure 7 represents the shape and structure of this polymer. You know this. This is DNA. So it's got a double helix. We need to just describe the shape. And there we go, double helix shape. It's made up of 2 polynucleotides made up of many nucleotide monomers joined together to form polymers. Sugar phosphate backbone would get you a mark. It's got hydrogen bonds between complementary base pairing, A to T, C to G, if you want to talk about that. Each individual nucleotide has a nitrogenous base, a phosphate group, a sugar. You can call the sugar pentose or deoxyribose. So loads and loads of different points you can get on this about the structure of DNA. Easy peasy. Let's move on.
Keep moving on, keep moving on, keep moving on, keep moving.
Okay, this question is about a reversible reaction, the reaction between solutions of iron 3 ions, iron 3 plus, and thiocyanate ions, SCN minus, and it's reversible. The ionic equation for the reaction is Fe3 plus yellow goes plus SCNI, or CN minus colorless goes to FeCN2 plus red. The color of the equilibrium mixture at room temperature is orange. So when there's an equal amount of reactant yellow and reactant red, it's orange. Give the name of the solvent used to dissolve the ions in this reaction. Well, if you look, they have aqueous symbol AQ next to all of the reactants and the product on the right hand side as well. What does AQ mean? It means it's been dissolved in aqua, in water. There we go. Right, a few drops of colorless solution containing a high concentration of thiocyanate ions are added to the equilibrium mixture. Explain the color change. So if you add SEN minus ions, you're going to force it to go, you're going to cause the equilibrium to shift to the right. You've added SCN minus. By Le Chatelier's principle, the reversible reaction will try and counter that change and shift the equilibrium to the right, producing more of the red color. So we're going to see the color go from yellow, more towards red. Right, 10.3. A water bath is set up at room temperature, above room temperature. When a test tube containing the orange equilibrium mixture is placed in the water bath, the mixture becomes more yellow. Explain what this shows about the energy change. Well, if the mixture has become more yellow, it's shifted to the left-hand side when we did a temperature increase. So if we did a temperature increase, and the change tried to counter that temperature increase by shifting to the left, it means the left-hand side would be the endothermic direction. So when you increase the temperature, the equilibrium shifts in the endothermic direction, which was yellow. What does that tell us about the forward direction? The forward direction must be the opposite, must be exothermic. So this proves the forward direction is exothermic. And that's going to get you your 3 marks. Right, let's look at the next question. Explain why a change in pressure does not affect the color. So if we go up and look at the reaction, you will see there are actually no gases involved in this one. So as there's no gases involved, a change in pressure will not affect the equilibrium, because normally if you increase the pressure, it goes to the side with the least gas molecules, or if you reduce the pressure, it goes to the side with the most gas molecules. There's no gas molecules in this reaction, so changing the pressure will have zero effect, as there's the same amount of gas on each side, which is 0. So there'll be no effect because there's no gases. Other metal ions form colored equilibrium mixtures with thiocyanate ions. Which metal would form a colored equilibrium mixture? So this is testing you on your old transition metals. Transition metals form colored compounds. So which of these are transition? Well, the first one's group 3. Magnesium ions are from group 2. Sodium ions are from group 1. So it is the middle one, which is a transition metal. I mean, that's got a CO, the symbol, CO3 plus, is that, or 2 plus? My eyesight's so bad. That looks like cobalt, to be honest. So it's what, if you look in your periodic table, it's in the middle. It's a transition metal. And that's it, guys.
You're
Let's
still
get to the
here?
mark.
It's over.